Welcome back, class. So we were learning about the feedback and stability. Last time I have given an overview of these things, and we ended at the thing that basically feedback can be categorized into two types: positive feedback and negative feedback. In the negative feedback, basically what is happening, the portion of the output signal, okay, like you have input, you are getting some output, so the portion of the output signal will be subtracted, okay, from the input. Okay, for example, let's say this is output signal is multiply with beta, so here we will use the subtractor, so we will get input signal minus, okay, subtraction of the portion of output signal. Okay, this will be the negative feedback, and in the positive feedback we will have the summer here, so we'll get the summation here. That will be the positive feedback. We mostly use the negative feedback for the design of the op-amps, amplifiers, and the positive feedbacks is basically mostly used for the design of the accelerators, generators. Okay, so usually we use this. And the focus of this chapter and in this course we will be putting more focus on negative feedback. Okay, so we will see this negative feedback in more details. Okay, so let's have a look at the generalized feedback amplifier network. Okay, so what are the let's say we have a source and it is producing a signal as I. Okay, and let's say the open loop gain, okay, of the amplifier or amplification factor is A. Okay, so we like have an amplifier which has a gain of A, and the input signal is going to the amplifier and you are getting an output signal. Okay, now we want to make a feedback network. So what will we do? We will take the output signal and it will be fed back to the input. Okay, so and here we place a block which is beta. Beta is called basically the feedback transfer function. Okay, beta is called feedback transfer function. Do not mix this with the current gain of the amplifier. Okay, this is the feedback transfer function. So basically what is happening, you are getting output which is multiply with beta. So basically as feedback which you are getting here, it will be beta times of S naught. Okay, so this is the portion of output. This is not complete output. Beta could be 1 or any factor. Okay, and then it's going to the input. Okay, so here we are having the subtraction of the input and the portion, okay, which is coming from the input. So basically the error signal which we will get, it will be the subtraction of input minus this feedback output, okay, which is basically the multiplication of beta with S naught. So this is my error signal. Okay, so basically if you want to go for the stability, okay, you want to get a stable output, okay, and if we have some variations, so input, it will be basically continuously changed according to the feedback. So basically this error signal which we are getting here, that will be fed into the amplifier. Okay, so amplifier will be adjusting its amplification accordingly until we are getting a stable output. Okay, so like if the difference between input and the feedback is almost zero, it means error is zero, so we are actually approaching towards a stable system. Okay, so this is a basic feedback network. Okay, now here what are the other things if you focus here now? So if you take the ratio of output, our inputs, this we call this A. Okay, basically if you take the ratio of output, our input here, that will be our closed loop transfer function. Okay, that will be our closed loop transfer function. Okay, because we get a closed loop here. Okay, this is called AF. Okay, and if you take the ratio of the output our error signal, that will be our amplifier. Okay, so now let's just have a look here what we are actually getting here. Okay, now if you write this equation, output is basically A times of error signal, right? And what is your error signal? You just write here, that is A times Si minus beta times S naught. Okay, or we can write this ASI minus beta times S naught, right? Or like if you just rearrange this equation, okay, so we can take this the other side, so it will be S naught plus A beta S naught is equal to A times Si. Okay, so if you take S naught common, why I want to take this ratio? Okay, 1 plus A beta times A Si. So the ratio of output over input, it will be A over 1 plus A beta. That is basically our closed loop transfer function. Okay, ratio of output over input is A over 1 plus A beta. A is what? Open loop gain. Okay, of only transfer function. Okay, and the product of A times beta, this is also called loop gain. Okay, so I can also rewrite this as A over 1 plus T. So T is basically my loop gain factor here. Okay, so this is the important output here which we are getting, that the closed loop transfer function is A over 1 plus beta A or A over 1 plus T. T is called, beta is called the loop gain. This is very important, very important. And basically loop gain is what? The the ratio of the feedback divided by the error signal. Okay, so if you just like derive them, okay, you will get this. The ratio of the feedback over error signal basically is our loop gain. Okay, so these are the terms which you guys have to remember now. Okay, from this chapter. A is the open loop transfer amplifier gain only. Okay, beta is the feedback transfer function. Okay, not the current gain. AF is the closed loop transfer function, which is A over 1 plus beta A. Okay, and T is the loop gain. Now here there are certain things. Okay, now for example, you want to write the closed loop depending on frequency, for example omega. So we can write this as A will be the function of frequency 1 plus beta, and this A will be the function of frequency. So this will be the closed loop gain with the dependency on the frequency. Okay, and we assume that T is basically a positive. T will be positive for the negative feedback system. Okay, and there is one more assumption here. Usually we know that usually your error signal is very small. Okay, very small. Okay, so if our error signal is very small, okay, what does this mean? Okay, we know that basically as feedback our as error signal is basically T. Okay, or and if this is very small, okay, very small number, okay, so it means 1 over very small number. Okay, for example 0, so 1 over 0, okay, so that will be infinity. Okay, so if this is very small, it means T will be very large. Okay, for example T is 1000, so if we have 1 plus T, that will be 1001, approximately is equal to T. So basically this equation can be simplified to A over T only. Okay, because 1 plus T is approximately T, or A over what is T? Beta times A will be cancelled, so 1 over beta. Okay, so if your error signal is very small, then the transfer function will be just the inverse of the closed loop transfer function, feedback transfer function. Okay, AF will be 1 over beta only. Okay, if error signal is very small. So these are just the some simplification assumptions here. Okay, so basically this feedback network, okay, like you have seen in the op-amps, okay, usually it consists of the resistive, capacitive, inductive or diodes. Okay, these components. Okay, so it means that the feedback amplifier gain, okay, feedback amplifier gain, okay, it only depends on the elements, okay, not the internal parameters of the transistor. Okay, like if you are going for this, okay, so closed loop transfer function, okay, it will be depending on the these parameters. Okay, because usually we have these parameters in the closed loop in the feedback. Okay, so that's why it will not depend on the internal parameters, so it will make it independent. Okay, for example in the op amp we know that it is closed loop gain is what? Minus R2 over R1. So it is only depending on resistors, not on the internal beta, G, M, K and values. Alright. So this is our view about the basic configuration and working of the feedback amplifier. Okay, so this equation is important. Okay, so this is just that assumption here. Okay, what we have just did, and the error signal is small. Okay, examples we will see in the live session. And other thing is which is basically advantage of the feedback network, that the gain sensitivity. Okay, so basically we are trying to find out how much change in the gain will occur with the feedback network. Okay, so we know that the overall closed loop gain of the feedback amplifier only depends on the feedback network. Okay, only. Okay, for example, we know that it approximately is 1 over beta, okay, or a over 1 plus t. So it is depending on the feedback network components. Okay, now we want to take what will be the change in gain. So we will take the derivative of this. Okay, we will take the derivative of this equation. Okay, which is basically AF is a over 1 plus beta a. We want to analyze gain sensitivity. What is the change in gain? So we will take the derivative of this with respect to a. So if you just apply the derivative rule, okay, like u over v, which will be basically v square u v derivative minus u v derivative. Okay, so if you apply, we will get this equation. Okay, our original equation is what? This one. Okay, this is our original equation. Okay, now here if you just do some more simplification, okay, and if you like just put up try to replace this equation in here and do some more simplification, what will we get? We will get this equation. Okay, that the change in gain, okay, with respect to the gain value, it will be the change of gain, open loop gain, multiply with the closed loop gain divided by the open loop gain. Okay, so basically the percentage change in the closed loop gain is less than corresponding percentage change in the open loop gain by a factor of 1 plus beta I. Okay, so basically what is percentage change in the closed loop gain is lesser than the change in the open loop gain by a factor of 1 over beta A. Okay, so that is the main equation which we are getting here. So the gain sensitivity we can analyze by using this formula. Okay, see the relevant example in the live session. And similarly, if you want to go for the bandwidth extension, okay, so let me stop here for this case and we will see the relevant example and the other things in the live session. Thank you very much for your time.